lesson 7.1, we're going to look at polynomial functions. There's not a whole lot you need to write down here. You just need to kind of listen and follow along as I go through a lot of these worked out examples and define some things for you dealing with polynomial functions. But polynomial function, recall that a polynomial is a monomial or sum of monomials. Sum of monomials means like a binomial, 2 terms, trinomial, 3 terms. So they give you an example here of 3r squared minus 3r plus 1. That's a polynomial with one variable, because the only variable in it is r. But we can also look at other things here dealing with polynomials. We're going to look at the degree of a polynomial. The degree, and you need to know how to find the degree, so we'll look at that here. The degree of a polynomial is the greatest exponent of its variable. Okay. The leading coefficient is the coefficient on the term with the highest degree. So let's look at some examples here. Now these are different types of polynomials. We have a constant, which would just be a number term, 9. That is degree 0 because it does not have an x term. That would be like x to the 0 power. There's no variable term on it. Okay, if you have a constant term, it's that term of that, the degree of that term is 0 because there's no variable on it. So the lead coefficient would be 9. So that's with a constant or a number polynomial. Linear would be x minus 2. The degree is 1 because the exponent on x is a 1, so we call that degree 1. The degree of the minus 2 would be 0, but you take the biggest, to find the degree of the polynomial, you take the biggest degree of any term. So the lead coefficient is 1 because there is a 1 out in front of that x to the first. Quadratic, highest exponent is x squared, so they give an example of 3x squared plus 4x minus 5. We call that degree 2. If you look on it, the degree of this term is 2. Then you have the 4x, which would be degree 1, and the minus 5, which is degree 0. So the lead coefficient, so on the x squared, because this is a quadratic or degree 2 polynomial, the lead coefficient would be right here. It's 3. A cubic function. Here's an example of a cubic function, 4x cubed minus 6. So we only have a cubic term and a constant term, but the degree of that cubic term is 3 because the exponent's 3, so we say degree 3. Notice the lead coefficient, well, there's a 4 on that x cubed term. Now, they kind of generalize here, but that's how you want to find the degree of any term. So, let's look at some examples here. Finding degrees and lead coefficients. State the degree and lead coefficient of each polynomial in one variable. If it is not a polynomial in one variable, explain why. Okay, so if you look at this first example right here, 7x to the 4th plus 5x squared plus x minus 9. The only variable in it is x, so we say it is a polynomial in one variable. How do I find the degree? I find the biggest exponent, which is that 4 right there, so we say the degree is 4. The lead coefficient is the number in front of that x to the 4th term, so the lead coefficient is 7 because it's 7x to the 4th. If you look at the next example here, we have 2 variables involved in this. So it's not a polynomial in one variable because it has both x and y in it. So you can't, we're not going to find the degree of that then. C, if you look here at this one, things are not a polynomial when you have x in a denominator. That's what they state here, that this is not a polynomial. The term 1 over x cannot be written where n is a non-negative integer. Because this term, if you think about 1 over x, that's 1 over x to the first. That really means it's the same as x to the negative first. These exponents cannot be negative. Okay, that makes it not a polynomial. So if you have any x to a power in a denominator on the bottom of a fraction of any term, it's not a polynomial. Okay, if you look at the next one, is this a polynomial? We got 1/2 x squared, and it's okay to have coefficients that are fractions. We just can't have an x down in the denominator. Now, they basically write it in what we call decreasing order of the exponents or powers on x. Some people call that descending order of the exponents. So they rewrite it with the x to the 5th first, so it's negative 1x to the 5th plus 2x cubed plus a half x squared. So this is a polynomial in one variable. The degree would be 5 because my biggest exponent's 5. The lead coefficient is -1 because there's a -1 out in front of that x to the 5th term. A polynomial equation used to represent a function is called a polynomial function. For example, the equation f of x equals 4x squared minus 5x plus 2 is a quadratic polynomial function. Okay, quadratic is biggest degree is 2. That's what makes it quadratic. It's got x squared. This one, p of x equals 2x cubed plus 4x squared plus minus 5x plus 7 is called a cubic because its degree is 3. Other polynomial functions are defined by the following rule. If you know an element in the domain of any polynomial function, you can find the corresponding value in the range. Recall that f of 3 can be found by evaluating the function for x equals 3. If this is functional notation, this just means if you had f of x, that would mean you'd plug 3 into the function for x. That's kind of what they're stating there. Evaluate a polynomial function. So we look at this. Here's the given function. F of r equals 3r squared minus 3r plus 1. Find the values of f of 1, f of 2, and f of 3. So notice what happens if we're finding f of 1 right here. I plug 3, and this is kind of color-coded for you. I plug in for r, I plug 1. There's also an r there, so they plug 1 in there. So it's 3 times 1 squared. Well, 1 squared is 1. 3 times 1 makes that 3. Here I have 3 times 1, which is 3. And then I have the plus 1. 3 minus 3, that's 0. 0 plus 1, my answer is 1. If you plug 2 in, if I find f of 2, I'll do the work up here for this one. So I have 3 times 2 squared minus 3 times 2 plus 1. Now notice order of operations says you got to square first, so that's 4. 3 times 4 would be 12. Let's do this multiplication next. Minus 6 plus 1, which is what they did right here. And 12 minus 6 is 6. 6 plus 1 is 7. So there's your answer for that one. F of 3, they did a similar thing. Notice when you get this, you have to do the 3 squared first, which is 9. 3 times 9 gave that 27. 3 times 3 here is 9, so it's minus 9 plus 1. 27 minus 9 is 18. 18 plus 1 gives the 19. So they're just plugging in the value. Okay, now what's going to change is when you plug in not a numeric value, which you're more familiar with. Now notice what they say. Find p of a squared given this function. So p of x equals x cubed plus 4x squared minus 5x. And they want me to find p of a squared. So well, the key thing is you're not putting a number like 2 or 3 in there for x. I'm putting in a squared every place I see an x and then following order of operations. So it would be a squared, but now there's a power on that x. So it's a squared in for x right here, cubed. Here 4, and then we put a squared in for x. I'm going to put it inside parentheses, but then the power on that is squared minus 5 times a squared. Well, power to a power, I multiply exponents, so that's a to the 6th. Power to a power here, multiply exponents, that's a to the 4th, so it's plus 4a to the 4th. Here I'm just multiplying 5 times a squared, so that's minus 5a squared. There's no outside power here, or it's 1, so it's just 5a squared. I cannot simplify this expression anymore. There are no like terms. I can't put those terms together. So when I substitute in some type of variable expression for functional notation, I'm going to get an expression out of the function. Okay, and you can just combine like terms. Now, when they go into a little more detail, it gets a little harder. Find q of a plus 1 minus 2 times q of a given this function for q of x. So let's look at what they did here. And I'm not going to write this one out, but follow along. Notice they color code it in this line right here. Okay, so in for this x right here. use a different color here. But in for this x right there, notice they put a plus 1 in there. And that is squared. So they have to do the binomial squared. These three terms come from squaring that binomial. If you do, I'll do it off to the side here. If I had a plus 1 squared, remember that's a plus 1 times a plus 1. So that's a squared plus 1a plus 1a plus 1, or a squared plus 2a plus 1. That's where these three terms right here came from. Okay, then minus or plus 3 times a plus 1, so I have to distribute right there. That's where the 3a plus 3 came from. And then I had the plus 4. And all they do then to go to this line right here is combine like terms. So I have the a squared, that takes care of that term. I'm going to put the 2a and the 3a together. That's where the plus 5a comes from. And then I have 1, 3, and 4 all positive put together. And there would be my answer. So I'm putting in a binomial in for x. So I had to use the distributive property. I had to FOIL or square a binomial when I did that. To evaluate 2 times q of a, here's what they do. They do 2, that's this 2 right here, times q of a. Now if I put a in for x right here, it's just a squared, so the a replace the x, plus 3a plus 4. And then you basically distribute your 2, so it's 2a squared plus 6a plus 8 when you distribute. Now they're doing, what did we get from this function? Well, that's this answer right up here. A squared plus 5a plus 8, that was this answer from q of the binomial a plus 1. And then we subtract off what we got when we did 2 times q of a. Now you have to distribute your opposite sign, so all these algebraic properties are coming into play. And that changes each of these signs. And then you just look at this line right here, and we want to combine like terms. So a squared minus 2a squared is negative a squared. Plus 5a minus 6a is negative a, that's that term. And notice the plus 8 and minus 8 drop out. So that whole thing, taking q of a plus 1 and subtracting off 2 times q of a, evaluates or simplifies down to negative a squared minus a. Okay, a lot of algebraic steps involved there. Alright, now we're going to look at the graphs and kind of some characteristics of the graphs of polynomial functions. The general shapes of the graph of several polynomial functions are shown below. These graphs show the maximum number of times the graph may intersect the x-axis. Recall that the x-coordinate of a point at which the graph intersects the x-axis is called a zero of a function. The x-intercepts are the zeros, or the roots of the function, whatever you want to call it. How does the degree compare? So let's ask ourselves this question. How does the degree compare to the maximum number of real zeros? Remember, a constant function is a horizontal line. Its degree is 0. Notice the number of real zeros, there are none. It doesn't go through the x. Remember, a real zero occurs where it goes through the x-axis. 0 degree, no real zeros. Doesn't go through the x-axis. A linear function, okay, is a line. The degree is 1. Notice it has at most 1 real zero, 1 intercept. For a quadratic function, degree is 2, so it's like you got x squared. So at most 2 real zeros. Notice when we say real zeros, that's the how many times at most, how many times can it go through the x-axis? 2. Over here is an example of a cubic. Cubic functions are degree 3, means we got x cubed on there. At most 3 zeros, or 3 x-intercepts. Notice this one does. Now, not all cubic functions will have that many. That's the most it can have, though. Okay, a degree 4 function is called a quartic function. At most 4 real zeros. Now, do all quartic functions have 4 real zeros? No. That's the most they can have, though. They could have less than that. Quintic means degree 5, at most 5 real zeros. And this one actually does have 5 real zeros. So at most 5 real zeros. Do they all have 5? No, they could have less than that. So notice the shapes of the graphs for even degree functions and odd degree polynomial functions. So that's what they want us to look at now. Okay? Even degree would be, for example, this right here is even, and the quartic would be even. Okay? And then we have odd, would be like degree 1. This would be odd over here. Quintic would be odd. Okay, those would be odd degrees. The degree and the lead coefficient of a polynomial determine the graph's end behavior. When we talk about the end behavior, what's happening as x goes to positive infinity? Okay, in other words, as I go far to the right, and as x goes to negative infinity, or as I go infinitely to the left, so far to the left. What's the end behavior? Now, here's what I want you to notice. Let's look at this quadratic, because we're real familiar with parabolas. Notice the end behavior. As I go infinitely out that way and infinitely out that way, the graph is going up, or the function's going up in both directions. They're the same end behavior. They're both going up. Now, we can have parabolas that go like this, but the key is the end behavior on both sides is the function's going in the same direction, either both up or both down. Notice the other even degree, a quartic function. Notice that is either the end behavior, in this case, is both up for this one's pictured, but you could have one that's upside down, that goes like this. Well, the end behavior, now we're going, as we go infinitely to the right or to the left, the function is going down. Notice with odd degrees, do you see how the end behavior is opposite? Here, this graph is going up. This would be the cubic function. This one's going down. Now we're going in opposite directions as I go out. Same thing here with the quintic function. The degree 5, opposite end behavior. One's going up, one's going down. And that's key, what we're going to look at here. All right. So, the degree for an even, if the lead coefficient is positive, basically that means the end behavior, and this is kind of the notation you have to get familiar with, this means what the function does, what the graph does. F of x goes to positive infinity. So, if the lead coefficient is positive, meaning, let's say you had x squared, f of x equals x squared. If it's positive, it's going up. The function is going to positive infinity as x goes. Now this really means as x goes to negative infinity, going that way, or as x goes to positive infinity, what's the function doing? Well, it's going infinitely up. That's why we say the function is going to positive infinity in both directions. If the degree is odd and the lead coefficient is positive, it means on the right side, the graph's going to be going up, and on the left side, it's going to be down. Remember, with odd degrees, the end behavior is in opposite directions. If it's a positive lead coefficient, in other words, whatever that highest degree term is, positive, it means, look at what the end behavior is on this side. The function is going infinitely up as we go infinitely out in the x direction. And it's reversed on this side. The graph is going infinitely down. That's what this says. The function is going to negative infinity as we go out infinitely in the x direction to the left. And then it's just reversed here for degree even. If it's negative, now the end behavior is going to be going down or to negative infinity on the graph as x goes infinitely to positive infinity or negative infinity. And it's reversed if there's a negative in front of an odd degree. Okay? Now, as we go to the right, okay, as we keep going to the right, the function is going down. As we keep going to the left, the function is going up. So, we'll continue with this on the second part of the video.